So hi everyone, in this video I will discuss the last short channel effect, that is the gate leakage. Okay, so firstly I consider here the NMOS. In case of the long channel, the distance between source and drain, it is very far away, and till now what we know already, the gate current, it will be always zero. That thing I know already. Okay, and this is the oxide layer, that is the silicon dioxide. This is the silicon dioxide, and this is the thickness of the silicon dioxide, TOX. TOX is the thickness of silicon dioxide. But when we brine the drain near to the source, then this is the short channel. In case of the short channel, if we reduce the channel length, then effectively the oxide of thickness is also reduces comparatively the long channel. So in the long channel, the oxide of thickness is more comparatively the short channel. And in the short channel, in the short channel, the TOX is less the compared to the long channel. Okay, so I am telling like that, effectively the oxide thickness is also decreases in the short channel. If oxide thickness is decreases, then due to the tunneling, the some electron due to the tunneling process, the some electron will go to the gate side, and the gate current will exist. Means the gate current will not equal to zero in case of the short channel. Why? Because of that, when we reduce the length between the source and drain, means when we bring drain near to the source, then the channel is reduces effectively. The oxide thickness is also reduces. If oxide thickness is reduces, if oxide thickness is reduces, then due to the tunneling process, some electron will go, yeah, jump into the gate side, and gate current is existed. Gate current is not equal to zero. So this is the gate leakage. Okay, so this is the not good thing. This is the not good. Because of that, the advantage of the NMOS, yeah, MOSFET is gate current, it should be always zero. So this is not a good. Gate current exists. So how we can avoid this thing? So someone asked like that one question. So sir, COX capacitance per unit area. If I write the EOX, that is the epsilon divided by TOX. So someone asked like that. So sir, when we if we reduce the TOX in the short channel, no issue, then the gate current will not exist. Yeah, okay. If you increase the TOX, then effectively the oxide capacitance, this oxide capacitance will decrease it. This oxide capacitance COX will decrease it. So this is not good, no. Actually we want the our desire is like that, the oxide capacitance should be constant. Oxide capacitance should be constant. So in the short channel, if we increase the TOX, oxide thickness, the oxide capacitance will decrease it. So this is not good. But our desire, we want like that, the oxide capacitance should be constant. So instead of the silicon dioxide, I use another. So to avoid, yeah, to overcome this issue, we use the another the oxide, that is the hafnium, that is the name, hafnium dioxide. Okay, hafnium dioxide I use. Hafnium dioxide, that is the HFO2, and it is also called the high K dielectric. High K dielectric we use instead of the silicon dioxide, we use the high K dielectric. The permittivity of, so the relative permittivity of the high K dielectric is 12 compared to the silicon dioxide. Silicon dioxide is the permittivity is only 3.9, yeah, approximately 4. So now if we go for the COX, that is the E epsilon divided by the TOX. Now, so how this is possible? We want the oxide capacitance should be constant. If oxide capacitance should be constant, for that purpose, if we use the high K dielectric instead of the silicon dioxide, then the permittivity is the greater than the 3. Actually, the permittivity of, relative permittivity of the high K dielectric, that is the hafnium dioxide, is 12. That is the 3 times. If we use this, the oxide thickness is also increased. If these two things is increases, the oxide capacitance will not change, it will constant, it will behave as like that, the constant. So the designer, so don't worry, so designer not worry about the gate leakage. If we use instead of the silicon dioxide the hafnium dioxide, that is the high K dielectric, then the gate current will be zero. Okay, gate current will not exist, effectively gate current will be zero. So this is all about the gate leakage, this is all about the gate leakage. I hope you understand. Okay, so I am telling again, if you have any issue, so just I'm telling, in case of the long channel, in long channel the gate current is always zero, that thing I know. Okay, okay, but in case of the short channel, when we reduce, when we bring the drain near to the near source, then in this case, then in this case the channel length is reduces. If the channel length is reduces, then the oxide of thickness is also reduces. If oxide of thickness is reduces, then due to the tunneling process, some electron of the channel will go into the gate side and gate current will exist, gate current is not zero. So this is the disadvantage. How can we avoid this thing? So someone asked like that, if we increase the oxide thickness, if we increase the oxide thickness in short channel effect, if we increase the thickness of oxide in short channel, then the effectively oxide capacitance will decrease it. Then that thing I don't want. Oxide capacitance should be constant. So instead of the silicon dioxide we use the high K dielectric, that is the hafnium dioxide, whose relative permittivity is approximately 12. Okay, which dielectric constant, that is the relative permittivity 12 compared to the silicon dioxide. Silicon dioxide approximately 4. So if we increase this thing, no, if we increase the 3 times 2x, and if we use the high K dielectric instead of silicon dioxide, the oxide capacitance remains constant, because it increases the 3 times, it is also increases the 3 times. So no effect on the oxide capacitance. And if the oxide thickness is increases, then the gate current will be zero. I hope you understand. Okay, in the next video we will meet in the next topic. Thank you.